Okay, so we have just discussed about the traction vector. If it is acting on some plane labeled with the S, then we use the superscript. Now consider the small differential volume, rectangular parallelepiped kind of volume. Okay, so we see that okay, three faces are visible. So we assume that this distance is delta y, this distance is delta x, and this distance is delta z, which are different in general, but they are very small quantities. So if you wish, you can shrink it to a point. So what we assume that okay, these faces are visible. So on these faces, these three traction vectors are acting. We say that okay, this is the face on which the x-axis is the normal. So we give a name. We say that it is a positive x-plane. Here it is the face on which y-axis is the normal. Okay. So this the outward unit normal drawn on this face coincides with the y-axis, same direction. That is why we say that it is a positive y-plane. Here the same thing is valid. That means the outward unit normal is aligned with the positive z direction. That's why a positive z plane. You see the face which is not visible directly hiding. That means the parallel to this z plane. Okay, plus z plane. So we say that okay, this is the plane. So whose outward unit normal is opposite to z direction. So we use that negative, this term negative z plane. Therefore we can see that okay, this plane negative x plane. Okay, and here the back side, it is basically negative y plane. Okay, so on the negative x plane, negative y plane, and negative z plane, the traction vectors are also working. So here this traction vector Tx, T is the traction and it is acting on the x plane. So it can be further resolved into three parts. One in the Cartesian part, that means along the x, y and z direction. So what we say that okay, we give a name. We say that this one okay is sigma x x, and this one sigma x y, sigma x z. So we are basically using this representation. Okay, so components are identified with two labels, two indices. The first one you see everywhere x is appearing, so that that represents that says that the t vector, the traction vector, is acting on the x plane. So first one is the plane, second one is the direction. Okay, first one is the plane, second one is the direction. So same thing we can follow for the other tractions. Sigma yx, sigma yy, sigma yz, and for tz we say that sigma zx, sigma zy, sigma zz. Okay, this way we resolve the components. Now this can be written in a compact manner, this way, in a matrix form. Okay, so we write in a matrix form. So where these rows you see, they are basically the entries of these tractions. We have three planes, okay, mutually orthogonal planes. So these are the components of Tx, these are the components of Ty, and these are the components of Tz. So when we write in this form, we say that the diagonal entries, these three, they are the normal stresses, whereas the off diagonal entries, we use a special name that they are the shear stresses. So we say that the normal stress is positive when it is acting on the positive plane and the direction is in the positive direction, okay? Or if we consider the traction on the negative plane, then we say that sigma xx is positive if it is acting in the negative x direction, okay? So that means first one is the plane on which it is acting, second one is the direction along which it is acting. So you see the sigma, this should be sigma y x, sigma y y, sigma y z. So here you see sigma z z, sigma z y, sigma z x. So it is the positive z plane, positive direction, positive. Positive z plane, positive direction, positive. So if you consider the other plane, what happens? You see the a different direction. For example, if we just consider the bottom plane, the bottom part, okay. So if you wish to represent or identify the stresses at the plane, on that plane, so it would be sigma zz and sigma zx, sigma zy. Okay. So positive plane, positive direction, positive; negative plane, negative direction, positive. Okay. Or other situation, you get the negative value. Now consider a special situation. We say that it is a plane stress situation. So plane stress situation means one of the directions, axis directions, there won't be any stresses. So one of the planes would be stress free. You remember, just recall the previous diagram where we consider the parallelepiped, rectangular parallelepiped kind of object, infinitesimal differential volume element with 6 faces. Okay, so we saw that, okay, you can identify positive x plane, you can identify negative x plane, positive y plane, negative y plane, positive z plane, negative z plane. So here we say that we have a special situation where z plane is the stress free plane. That means this is the z plane, this is the positive x plane, back side is the negative x plane, positive y plane, back side is the negative y plane, this is the positive z plane, this face, the other side is the negative z plane. Here is the chosen reference axis. It is the horizontal axis is x, vertical axis is y. Here you are looking from along the, your line of sight is along the z axis direction, okay, negative z direction. You see x plane, you have two stresses, sigma xx, sigma xy. Y plane, you have two stresses, sigma yy, sigma yy and sigma yx. So other planes, you can identify that these would be opposite direction, sigma xx and sigma xy, or negative plane, negative direction is positive, it is maintained. This differential volume element is having this length delta x, height delta y and the width b. Now if we say that z plane is stress free, that means all the components associated with the z plane, they would be 0, okay, And if we consider the x plane, okay, if you there would be stresses like that, okay, but who is going to balance that? So we in our real life example, many situations you get that, okay, this x plane you get only two stress components, y plane you get only two stress components. So that is a special situation where these entries takes 0 all the time. So we say that this is a representation of plane stress problem, and you see 1, 2, 3, 4, 5, 6 entries are 0 all the time. So we use the reduced notation or matrix representation for plane stress problem. So in plane stress problem, here that is a geometric representation of these components. Okay, so now you see, if we consider the rotational equilibrium of this block, then rotation, say rotation about this point, okay, in this direction. So we write the equations of equilibrium, mi over o I, this is positive sum of all moments coming from the all the stresses or the forces or externally applied moments, if they are present, that sum should be 0. So this implies that, okay, let us see what happens. About this point, if we take a moment, that means about the z axis, if we take the moment, then we see that sigma y and this y, they are acting in the same line. So they cancel each other. So they do not have any contribution. These two stresses, they pass through their point, so they do not have any contribution. Same thing is true for the sigma xx. Only two guys are left. One sigma xy, the shear stress acting on the positive x plane. Another, the shear stress that is acting on the positive y plane. So if we account for their moments, so what we get? We get that, okay, forces acting on the positive x plane is estimated as sigma xy times the area, that means b times delta y. So this is the force that is acting on the positive x plane. So it has it is generating a moment, that means that amounts to the force multiplied by the normal distance. So here normal distance is delta x. Okay, and now we visit the positive y plane. What is happening there? The force that is acting on the positive y plane, that can be estimated as sigma yx times b times the length delta x. Okay, and it is generating a moment, sense is opposite, so that's why there you should take the negative sign. And how much is, what is the normal distance or the offset of the lever arm? That is delta x. And these two quantities must balance each other in order to maintain the rotational equilibrium. So what we see that, okay, this delta x is present in both the terms, delta y is present in both the terms, and b is also present. So we divide this expression by the volume. That means delta x, delta y and b. Okay, so we divide this expression by this and we get sigma xy minus sigma yx equals to 0. We get this expression. So that means sigma xy and sigma yx, they are taking the same value. Now you notice one thing, while deriving this expression, we assume some dimension, delta x, delta y, b. Now if we just check whether this relationship is valid at a point, the answer is whether it is true or not, then you will probably find that, okay, one observation, that if we take the limit, after arriving at that, if we shrink, if we take the limit delta x tends to 0, delta y tends to 0 or b tends to 0. So volume shrinks to a point, but still it does not involve any term related to delta x, delta y and b. So it is insensitive to that, that means it is valid at a point. So we say that stress this is shear stresses on two planes, they take the same value. This matrix is symmetric. That means if we consider sigma xx to be primary, the other one would be complementary. If we consider this one primary, then it would be complementary. They are symmetric. Same argument is valid when you go to the three-dimensional, when you go and check this three-dimensional state of stress. That means consider the previous differential volume, okay, containing 6 phases, containing 9 entries. That means these components are not 0, and then you take moment, you consider the rotational equilibrium about x-axis, about y-axis, and about z-axis respectively. You get 3 equations. So 3 conditions will tell that this entry, they are same, they will take same value, they are going to take same value, and these 2 entries, they will be taking the same value. Okay. So initially we have seen that this matrix is having 9 entries. Okay. Sigma, you see the indexes are different. Okay. However, once you satisfy or impose the rotational equilibrium condition, it would be having only 6 independent components. So we say that for 3-dimensional state of stress, 6 components are sufficient to describe the state of stress at a point. For 2-dimensional problem, plane stress problem, only 3 independent components are sufficient to describe the state of stress at a point. Okay. Now I go and consider the next problem.